Raman spectroscopy is a spectroscopic technique used to observe vibrational, rotational, and other low-frequency modes in a system. Raman spectroscopy is commonly used in chemistry to provide a fingerprint by which molecules can be identified. It relies on inelastic scattering, or Raman scattering, of monochromatic light, usually from a laser in the visible, near-infrared, or near-ultraviolet range. The laser light interacts with molecular vibrations, phonons or other excitations in the system, resulting in the energy of the laser photons being shifted up or down. The shift in energy gives information about the vibrational modes in the system. Infrared spectroscopy yields similar, but complementary, information. Typically, a sample is illuminated with a laser beam. Electromagnetic radiation from the illuminated spot is collected with a lens and sent through a monochromator. Elastic scattered radiation at the wavelength corresponding to the laser line is filtered out, while the rest of the collected light is dispersed onto a detector by either a notch filter or a band-pass filter. Spontaneous Raman scattering is typically very weak, and as a result the main difficulty of Raman spectroscopy is separating the weak inelastically scattered light from the intense Rayleigh scattered laser light. Historically, Raman spectrometers used holographic gratings and multiple dispersion stages to achieve a high degree of laser rejection. In the past, photomultipliers were the detectors of choice for dispersive Raman setups, which resulted in long acquisition times. However, modern instrumentation almost universally employs notch or edge filters for laser rejection in spectrographs, either axial transmissive, Cheney-Turner monochromator, or FD, and CCD detectors. There are a number of advanced types of Raman spectroscopy, including surface-enhanced Raman, resonance Raman, tip-enhanced Raman, polarized Raman, stimulated Raman, transmission Raman, spatially offset Raman, and hyper-Raman. Theoretical basis. The Raman effect occurs when electromagnetic radiation impinges on a molecule and interacts with the polarizable electron density and the bonds of the molecule in the phase and environment in which the molecule finds itself. For the spontaneous Raman effect, which is a form of inelastic light scattering, a photon excites the molecule in either the ground ρ vibronic state or an excited ρ vibronic state. This results in a molecule being in a so-called virtual energy state for a short period of time before an inelastically scattered photon results. The resulting inelastically scattered photon, which is emitted, scattered, can be of either lower or higher energy than the incoming photon. In Raman scattering, the resulting ρ vibronic state of the molecule is a different rotational or vibrational state than the one in which the molecule was originally, before interacting with the incoming photon. The difference in energy between the original ρ vibronic state and this resulting ρ vibronic state leads to a shift in the emitted photon's frequency, away from the excitation wavelength, the so-called Rayleigh line. The Raman effect is due to inelastic scattering and should not be confused with emission, where a molecule in an excited electronic state emits a photon of energy and returns to the ground electronic state, in many cases to a vibrationally excited state on the ground electronic state potential energy surface. If the final vibrational state of the molecule is more energetic than the initial state, the inelastically scattered photon will be shifted to a lower frequency for the total energy of the system to remain balanced. This shift in frequency is designated as a Stokes shift. If the final vibrational state is less energetic than the initial state, then the inelastically scattered photon will be shifted to a higher frequency, and this is designated as an anti-Stokes shift. Raman scattering is an example of inelastic scattering because of the energy and momentum transfer between the photons and the molecules during the Interaction. Rayleigh scattering is an example of elastic scattering. The energy of the scattered Rayleigh scattering is of the same frequency as the incoming electromagnetic radiation. A change in the molecular electric dipole electric polarizability with respect to the vibrational coordinate corresponding to the ρ vibronic state is required for a molecule to exhibit a Raman effect. The intensity of the Raman scattering is proportional to the electric dipole polarizability change. The Raman spectra is dependent on the ρ vibronic states of the sample. This dependence on the electric dipole polarizability derivative differs from infrared spectroscopy, where the interaction between the molecule and light is determined by the electric dipole moment derivative, the so-called atomic polar tensor. This contrasting feature allows one to analyze transitions that might not be IR active via Raman spectroscopy, as exemplified by the rule of mutual exclusion in centrosymmetric molecules. Bands which have large Raman intensities in many cases have weak infrared intensities and vice versa. For very symmetric molecules, certain vibrations may be both infrared and Raman inactive. In those instances, one can use a technique in elastic incoherent neutron scattering to determine the vibrational frequencies. The selection rules for inelastic incoherent neutron scattering are different from those of both infrared and Raman scattering. Hence, the three types of vibrational spectroscopy are complementary, all giving in theory the same frequency for a given vibrational transient, but the relative intensities giving different information due to the types of interaction between the molecule and the electromagnetic radiation for infrared and Raman spectroscopy, and with the neutron beam for IINS. History. Although the inelastic scattering of light was predicted by Adolf Schmeckel in 1923, it was not until 1928 that it was observed in practice. The Raman effect was named after one of its discoverers, the Indian scientist Sir C.V. Raman, who observed the effect by means of sunlight. Raman won the Nobel Prize in Physics in 1930 for this discovery, accomplished using sunlight, a narrow-band photographic filter to create monochromatic light, and a crossed filter to block this monochromatic light. He found that a small amount of light had changed frequency and passed through the crossed filter. Systematic pioneering theory of the Raman effect was developed by Czechoslovak physicist George Plaček between 1930 and 1934. The mercury arc became the principal light source, first with photographic detection and then with spectrophotometric detection. In the years following its discovery, Raman spectroscopy was used to provide the first catalogue of molecular vibrational frequencies. Originally, heroic measures were required to obtain Raman spectra due to the low sensitivity of the technique. Typically, the sample was held in a long tube and illuminated along its length with a beam of filtered monochromatic light generated by a gas discharge lamp. The photons that were scattered by this sample were collected through an optical flat at the end of the tube. To maximize the sensitivity, the sample was highly concentrated and relatively large volumes were used. Consequently, the use of Raman spectroscopy dwindled when commercial IR spectrophotometers became available in the 1940s. However, the advent of the laser in the 1960s resulted in simplified Raman spectroscopy instruments and also boosted the sensitivity of the technique. This has revived the use of Raman spectroscopy as a common analytical technique. Raman Shift. Raman shifts are typically reported in wave numbers, which have units of inverse length, as this value is directly related to energy. In order to convert between spectral wavelength and wave numbers of shift in the Raman spectrum, the following formula can be used. Whereas the Raman shift expressed in wave number, λ0 is the excitation wavelength, and λ1 is the Raman spectrum wavelength. Most commonly, the unit chosen for expressing wave number in Raman spectra is inverse centimeters. Since wavelength is often expressed in units of nanometers, the formula above can scale for this unit conversion explicitly, giving applications. Raman spectroscopy is commonly used in chemistry, since vibrational information is specific to the chemical bonds and symmetry of molecules. Therefore, it provides a fingerprint by which the molecule can be identified. For instance, the vibrational frequencies of CO, C202, and C303 were identified and assigned on the basis of normal coordinate analyses using infrared and Raman spectra. The fingerprint region of organic molecules is in the range 500 to 2000 cm-1. Another way that the technique is used is to study changes in chemical bonding, as when a substrate is added to an enzyme. Raman spectroscopy is a very efficient and non-destructive method for investigation of works of art. Identification of individual pigments and the degradation products leads to insights into the working method of the artist and allows to gain information about the original state of the painting at the time of its creation in cases where the pigments were degraded with age. Raman gas analyzers have many practical applications. For instance, they are used in medicine for real-time monitoring of anesthetic and respiratory gas mixtures during surgery, in solid-state chemistry and the biopharmaceutical industry. Raman spectroscopy can be used to not only identify active pharmaceutical ingredients, but in the case of multiple polymorphic forms, it can also be used to identify the polymorphic form of the API. For example, there are 4 different polymorphic forms of the API encased in a drug marketed by Gilead Sciences for cystic fibrosis. Both infrared and Raman spectroscopy can be used to identify and characterize the API which is used in the formulation of casein. In biopharmaceutical formulations, one must use not only the correct molecule, but the correct polymorphic form, as different polymorphic forms have different physical properties, for example, solubility, melting point, and Raman infrared spectra. In solid-state physics, spontaneous Raman spectroscopy is used to, among other things, characterize materials, measure temperature, and find the crystallographic orientation of a sample. As with single molecules, a given solid material has characteristic phonon modes that can help an experimenter identify it. In addition, Raman spectroscopy can be used to observe other low-frequency excitations of the solid, such as plasmons, manyons, and superconducting gap excitations. The spontaneous Raman signal gives information on the population of a given phonon mode in the ratio between the Stokes intensity and anti-Stokes intensity. Raman scattering by an anisotropic crystal gives information on the crystal orientation, the polarization of the Raman scattered light with respect to the crystal, and the polarization of the laser light can be used to find the orientation of the crystal. If the crystal structure is known, Raman spectroscopy is the basis for distributed temperature sensing along optical fibers, which uses the Raman shifted backscatter from laser pulses to determine the temperature along optical fibers. Raman active fibers, such as aramid and carbon, have vibrational modes that show a shift in Raman frequency with applied stress. Polypropylene fibers also exhibit similar shifts. The radial breathing mode is a commonly used technique to evaluate the diameter of carbon nanotubes. In nanotechnology, a Raman microscope can be used to analyze nanowires to better understand the composition of the structures. Spatially offset Raman spectroscopy, which is less sensitive to surface layers than conventional Raman, can be used to discover counterfeit drugs without opening their packaging, and for non-invasive monitoring of biological tissue. Raman spectroscopy can be used to investigate the chemical composition of historical documents such as the Book of Kells and contribute to knowledge of the social and economic conditions at the time the documents were produced. This is especially helpful because Raman spectroscopy offers a non-invasive way to determine the best course of preservation or conservation treatment for such materials. Several research projects demonstrated usage of Raman spectroscopy as a means to detect explosives using laser beams from safe distance. Raman spectroscopy has also been used to confirm the prediction of existence of low-frequency phonons in proteins and DNA, greatly stimulating the studies of low-frequency collective motion in proteins and DNA and their biological functions. Raman reporter molecules with olefin or alkyne moieties are being developed to allow for tissue imaging with SERS-labeled antibodies. Raman spectroscopy has also been used as a non-invasive technique for real-time, in situ biochemical characterization of healing wounds, and multivariate analysis of Raman spectra has enabled a quantitative measure of wound healing progress. Raman spectroscopy has a wide usage in studies of biominerals. Microspectroscopy. Raman spectroscopy offers several advantages for microscopic analysis. Since it is a scattering technique, specimens do not need to be fixed or sectioned. Raman spectra can be collected from a very small volume. These spectra allow the identification of species present in that volume. Water does not generally interfere with Raman spectral analysis. Thus, Raman spectroscopy is suitable for the microscopic examination of minerals, materials such as polymers and ceramics, cells, proteins and forensic trace evidence. A Raman microscope begins with a standard optical microscope, and adds an excitation laser, a monochromator, and a sensitive detector, or photomultiplier tube. FT Raman has also been used with microscopes. Ultraviolet microscopes and UV-enhanced optics must be used when a UV laser source is used for Raman microspectroscopy. Indirect imaging. The whole field of view is examined for scattering over a small range of wave numbers. For instance, a wave number characteristic for cholesterol could be used to record the distribution of cholesterol within a cell culture. The other approach is hyperspectral imaging or chemical imaging, in which thousands of Raman spectra are required from all over the field of view. The data can then be used to generate images showing the location and amount of different components. Taking the cell culture example, a hyperspectral image could show the distribution of cholesterol, as well as proteins, nucleic acids, and fatty acids. Sophisticated signal and image processing techniques can be used to ignore the presence of water, culture or media, buffers, and other interference. Raman microscopy, and in particular confocal microscopy, has very high spatial resolution. For example, the lateral and depth resolutions were 250 nanometers and 1.7 micrometers, respectively. Using a confocal Raman microspectrometer with the 632.8 nanometers line from a helium-neon laser with a pinhole of 100 micrometers diameter. Since the objective lenses of microscopes focus the laser beam to several micrometers in diameter, the resulting photon flux is much higher than achieved in conventional Raman setups. This has the added benefit of enhanced fluorescence quenching. However, the high photon flux can also cause sample degradation, and for this reason some setups require a thermally conducting substrate in order to mitigate this process. Another approach called global Raman imaging uses complete monochromatic images instead of reconstruction of images from acquired spectra. This technique is being used for the characterization of large-scale devices, mapping of different compounds and dynamics study. It has already been used for the characterization of graphene layers, J-aggregated dyes inside carbon nanotubes and multiple other 2D materials such as MOS2 and WSE2. Since the excitation beam is dispersed over the whole field of view, those measurements can be done without damaging the sample. By using Raman microspectroscopy, in vivo time and space resolved Raman spectra of microscopic regions of samples can be measured. As a result, the fluorescence of water, media, and buffers can be removed. Consequently, in vivo time and space resolved Raman spectroscopy is suitable to examine proteins, cells and organs. Raman microscopy for biological and medical specimens generally uses near-infrared lasers. The use of these lower energy wavelengths reduces the risk of damaging the specimen. However, the intensity of near-Raman is low, and most detectors require very long collection times. Recently, more sensitive detectors have become available, making the technique better suited to general use. Raman microscopy of inorganic specimens, such as rocks and ceramics and polymers, can use a broader range of excitation wavelengths. Polarized analysis. The polarization of the Raman scattered light also contains useful information. This property can be measured using polarized laser excitation and a polarization analyzer. Spectra acquired with the analyzer set at both perpendicular and parallel to the excitation plane can be used to calculate the depolarization ratio. Study of the technique is useful in teaching the connections between group theory, symmetry, Raman activity, and peaks in the corresponding Raman spectra. Polarized light only gives access to some of the Raman active modes. By rotating the polarization you can gain access to the other modes. Each mode is separated according to its symmetry. The spectral information arising from this analysis gives insight into molecular orientation and vibrational symmetry. In essence, it allows the user to obtain valuable information relating to the molecular shape. For example, in synthetic chemistry or polymorph analysis. It is often used to understand macromolecular orientation in crystal lattices, liquid crystals or polymer samples. It is convenient in polarized Raman spectroscopy to describe the propagation and polarization directions using Porta's notation, described by and named after Brazilian physicist Sergio Pereira da Silva Porto.